I am Daniel Figueiredo from the Federal University of Rio de Janeiro, and this is a joint work with two of my students, Leonardo Ribeiro and Pedro Savarese. Neither of them could be here today, so I'm presenting the work. So the title is Struct2Vec, and the session is about node embeddings. So you'll hear again about one other technique to do it, but you will see along the talk that the approach is somewhat different. So let me start by recalling the problem. What are we trying to do here? So what are node representations? So node representation, the problem is actually to map nodes of a network into a space, usually Euclidean space. The problem is also known as network embedding, and it has been studied for more than 20 years in different, let's say, contexts. So here's my network, and the goal is to place each node of this network in Euclidean space. And there are many ways to do that. So here's one way that you could do it. Each node here received two coordinates in this 2D space. Here's another way to do it. And here's yet a third way to do it. So these are all different ways to embed nodes from this network into Euclidean space. So which of them is correct? Which of them is right or which of them is wrong? Okay, so the first one, it seems to be preserving network distances. So the distance between nodes in the Euclidean space is more or less similar to the distances between nodes in the network. For example, this guy here and this guy here are 4 hops away, and they are quite far in the embedding. The second embedding seems to be finding cliques. It put together nodes that actually belong to cliques. So here we have a clique of size 3 and an almost clique of size 4, and they're kind of close here together. And the third embedding seems to be preserving degrees. So here we have this little cluster with 3 nodes, and they all represent nodes of degree 3. Here's another little cluster of 3 nodes representing nodes of degree 1, the first one, of degree 3, this other one. So this embedding here seems to be preserving degrees of the nodes. Okay, so there are many ways to do it, and the right way to embed really depends on what you want to do with your embedding on the application. Okay, so another important thing for my work here, or for this work, is the structural identity of nodes. And this comes from the concept or the idea that nodes in networks have specific roles. You can think of individuals inside an organization, or web pages in the web, or proteins in a cell. These different nodes have different roles. And more often, these roles can be kind of identified through something that we call structural identity. It's not our term, it's something that's been around for, again, decades. And structural identity refers to the fact that nodes in the network can be identified just by the structure alone. So the structure gives them some kind of identity. And usually this identity that the structure provides is related to the role that they are playing inside the network. So structural identity can be seen as a proxy to identifying roles of nodes. So one form of very good structural equivalence or structural identity is automorphism. So here's a little network, and if you take a look, these 2 nodes, the red and the green node, are actually belong to an automorphism because you can switch the 2 around and relabel, recolor the remainder of the nodes and get the same network back. So red and green here belong to an automorphism. So similarly, but not quite the same, the brown and the purple node are actually structurally similar, but don't form an automorphism because their degrees are different. But they're clearly similar in structure. Okay? So this is the application that we're going to focus on. That's what the kind of things that I would like my embedding to preserve, the structural identity of nodes. Okay, so on the related work, we already seen throughout this session some of these things. So Word2Vec is a framework to embed words coming out of sentences into Euclidean space. It's a technique to embed words. So DeepWalk, as was just said, is an idea to embed network nodes generating sentences from random walks. It's a quite clever idea to run random walks on a graph, and the sequence produced by the random walk, I interpret that as sentences. Then we can use Word2Vec to embed the nodes that come out of this sequence. So Node2Vec uses a biased random walk to generate these sentences, so it improves a bit on deep walk by allowing the random walk to do a biased steps in the network. So what's important here is that in these two works, the random walk uses the original network to generate context, and we're going to do this differently very soon. So I should mention a third related work, which is roles, which uses the node-to-feature matrix to try to compute a low-rank matrix for roles, for the rows of the nodes in the network. So it's not really an embedding, but it's also trying to identify the rows of the nodes in the network. Okay, so let's get to Struct2Vec. So it's really a framework to embed nodes or to find node representations based on structural identity. And what we really want to do here is that two nodes that are structurally similar in the network should be close in the embedded space. I would like to preserve the identity of the nodes when I project them into Euclidean space. So the two key ideas behind the framework are the following. First is that structural similarity does not depend on hop distance. By this I mean that two nodes in the network might be neighbors, but they might be structurally very different. While at the same time, two nodes that are very far away from each other in the network could be structurally very similar. So Struct2Vec is going to be able to cope with that. The second key idea is that structural identity is a hierarchical concept. It's not something that's defined only according to the local context, but we're going to use a hierarchy of local contexts to say when two nodes are similar to one another, structurally speaking. Okay? And the last point is it's really a four-step procedure to be able to embed these nodes. And it's quite flexible because the operational aspects of each of the four steps can be changed or can be adapted as you wish. So I'm going to walk now through the four steps, focusing on the first two, which is actually where most of the novelty of the idea is at. So step one is about computing a hierarchical measure for structural similarity between two nodes. So I have two nodes in my network, and I would like to compute the distance between them. So for that, we're going to consider Rk of u to be the set of nodes that are at distance k from node u, R referring to the ring of nodes around u. And S of S is going to be the ordered degree sequence of a set of nodes S. Okay? So here's my network. If I pick this guy here to be node u, the ring of, let's say, zero ring around him is only himself, and he has degree 4. So that's the degree sequence of the first ring. So here's the second ring, the ring at distance 1 from him. It's composed of 4 nodes, and the ordered degree sequence of these 4 nodes is given here. 1, 3, 4, 4. Degree 1, degree 3, 4, and 4. So the next ring is this guy. These are all the 4 nodes at distance 2 from the Brown node. And the ordered degree sequence is a bunch of 2's because they all degree 2's. I can do the same thing for another node. Here's node V. The first ring is 3, then the next rings are 4, degrees 4, and the next ring degree 1, 2, 2, 2. Okay, so for every node, I have these rings that I can construct with the ordered degree sequence of the nodes in the ring. So what I'm going to do now is to use a metric to compare sequences. So G here is an edit distance, for example, from the first talk, or something else that compare the distances between two sequences. In our case, the sequences are degrees. And we're going to use a cost for pairwise alignment of this particular type, the max over the min minus 1. So if I try to align one element of the one sequence with the element of the other sequence, I'm going to pay a price which is the max over the min minus 1. And then we look for optimal alignment between these two sequences, and in the framework we chose dynamic time warping for this. But you could have chosen something else, including something from the first talk. So here's just a small example. The distance between the first ring of these two nodes is just 1/3, the maximum over the minimum minus 1. If I have these two sequences now to align, I can align them according to DTW, and I'm going to get a distance of 3.33, and so on. Here's the alignment of my next rings. Okay, now I really want to find a distance between these two that considers all these rings. So f of k of uv is going to be the structural distance between u and v considering the first k rings. So it's a recursive measure that I use the previous rings plus the added distance or the dtw distance of the current ring. Okay, so I'm building up these distances. So that's the step one. Construct a hierarchy of distances between two nodes given by this function here. One nice property of fk of uv is that if u and v are isomorphic, then fk of uv is 0 for all k. Okay, so it's really nice that we have this particular property. So here's the fk uv for u and v for the three values of k, 0, 1, and 2. Okay, and it's also a monotonic increasing function because g is always greater or equal than 0. So step 2 is to construct a multi-layer graph. And this multi-layer graph is going to encode the structural similarity between all node pairs of the network. So we're going to start by constructing a complete weighted graph for each layer. And each layer is going to correspond to a similarity hierarchy that I have just defined. So here's layer 0. It's actually a complete graph, but I'm only showing the edges incident to the brown node. And these edges here all have weights. And as you might be thinking, these weights are going to be inversely proportional to the structural distance at layer 0. Okay, so the weight is going to, between u and v, is an exponential function with a minus fkuv. So the closer they are, the larger is the weight. So in this example here, you see that node brown and node green have the same degree, so therefore in layer 0, they are quite close. I mean, this weight is going to be very high. We do that for every layer. Here's layer 1, and then all the way to the last layer, which in this example is layer 4. And then we connect corresponding nodes of the different layers. Okay, so here's the corresponding nodes of layer 0 with layer 1 with layer 2, and so on. Okay, so we have these edges going up and down the corresponding layers. So now I have this layered graph, which each layer is a complete graph, and every node in a layer is mapped to the corresponding layer, to the corresponding node in the layer below and above. Okay, that's step 2. Step 3 is to generate context for the nodes. So to generate context means to produce nodes that are similar to that node, structurally speaking. And to do that, we're going to use a biased random walk that's going to walk on this layered graph. So the random walk is biased, meaning that it prefers to go on edges that have higher weights. And recall here that the weight is high if two nodes are structurally similar. Okay? And we also can change layers to go up and down, and this means that I can look at a local or more broad context when looking for structural similarity. So we have a parameter p, which decides if I'm going to walk in the current layer or change layers. So if I walk in the current layer, I just take a biased step through one of my neighbors with probability, and this means that the random walk will prefer to move to more similar nodes. And with probability 1 minus p, I change layers. I either go to the layer above or below. And in this case, I prefer to go to layers with less similar neighbors. So if I'm in a layer where there are too many nodes similar to me, structurally speaking, I would prefer to go to a layer above where there might be less similar nodes to me, where I'm more unique so that I can find my context better. Okay? So the random walk is going to do that. So the fourth step is actually learning representation from this context. So what we're going to do is basically generate a set of independent and relatively short random walks using this graph, and we're going to call that the context for the node. You can think of it as sentences for the language, where the words are basically the nodes. So if I start in the brown node here in layer 0, I may move around, and I will produce a sequence of nodes that come out of a random walk here. And that's going to be the context for the brown node. And then using this context, we just train a neural network to learn latent representation for the nodes, giving the generated context. Okay? For example, we would like to maximize the probability of having nodes in the context given a particular node. So we could use, in our approach, we use skipgram for this, using hierarchical softmax, but you could use other language model or whatever other embeddings you like to embed context into Euclidean space. Okay, so that's the 4 steps of the approach. You might be wondering about complexity of this, because we're talking about complete graphs for every layer. So to reduce the time to generate and store the multi-layer graph, what we do is we apply 3 optimizations. The first one is to reduce the length of the degree sequence. The degree sequences can become very, very large as the rings grow into the network. So we compress them by putting in the degree sequence each degree that appears only once and the number of appearances of that degree. So we shrink the sequences. The second optimization reduces the number of edges in the multi-layer graph. So instead of comparing every node to every other node, I compare every node to just log n nodes. So I have log n edges in the multi-layer graph, and per node, sorry. And the third optimization is to reduce the number of layers in the multi-layer graph. Instead of going all the way up to the diameter, I can stop at, let's say, 3rd or 4th layer. Okay, with these 3 optimizations, the approach scales quasi-linearly, and we were able to run this on networks with more than 1 million nodes. Okay, so here are some results. Here's the barbell network. The barbell network is this little network here, and the identical colors represent nodes that are isomorphic to one another. Here's what DeepWalk would do. This is the embedding that DeepWalk provides, or an example, because if you run it more than once, you get different results. But this is a representative example. Here's what Node2Vec would do. And note that what they're doing is not quite what we want, because what we'd like to do is that all the nodes of the same color should be very close in the Euclidean space. What we'd like to do is to preserve structural identity. Okay, and here's what Rolex would do, or Rolls would do. So Rolls doesn't really produce an embedding, it produces rows, and it placed nodes in these particular rows here. And actually did a quite good job for some of the pairs. Okay, this pair, it spread the blue across 3 different rows. And here's 1 minute. Okay, and this is what Struct2Vec would do. Okay, so here note that all nodes of the same color are together, all the blue are here, all the reds, the 2 reds are here, the 2 yellows are here, so on and so on. So we actually brought together nodes that are isomorphic, automorphic in this network here. Okay, so isomorphic nodes were close in space. And this is similar results under optimization will be the same thing. Here's another toy example, the mirror-Cavalli network. So here's what Node2Vec would produce. DeepWalk would produce something very similar because they don't care about structural identity. Here's what Struct2Vec produces. So these 2 nodes here are isomorphic to one another, and they are here in Node2Vec, and they are here in Struct2Vec. These 4 nodes actually have the same role. They are the leaders of this group, and they are all over the place in Node2Vec, and in Struct2Vec, they are all together. So it seems that Struct2Vec can actually capture the idea of similar roles, putting them close in the Euclidean space. Okay? We can also use Struct2Vec for classification. So here's an example for airport classification, and this is actually good if the classification that you're trying to do pertains to roles of the nodes in the network. So we did this for air traffic network. We have airports and commercial flights. We did it for 3 networks, Brazilian, American, European. The labels are airport activity, low activity, medium, high, and high. We learned node representations using Struct2Vec and others, and use the representations to classify the airports. And note that in this step, no label information was used, okay? We just project the nodes into space and use that as features for classification. So we use node representations to train a classifier, a very simple one, logistic regression with L2 normalization, and here are the results. So here are the 3 different networks corresponding to the airports and commercial flights in these 3 places. The y-axis is the precision, the accuracy of the classifier. Here we see a Node2Vec and the degree as a feature having this performance, and this is what Struct2Vec would get, even under optimization. So clearly for the three cases, StructureVac has a superior performance. For the Brazilian air traffic network, we are 50% improvement. So just to conclude, structural identity is a concept of symmetry based on network and their structure. StructureVac is a flexible framework to learn representations for a structural identity. It's a multi-layer graph that encodes the structural similarity, and on this multi-layer graph, we can generate context that captures the structural identity. So it also helps classification when you have labels that are related to roles. And to me, it's yet another useful kind of embedding. It's not necessarily a substitute for others. It's doing something different. I just want to finish with one message, is that if you're trying to embed nodes into a clean space, you should try to look for the right embedding for your task. There's no one embedding that is correct. It depends really what you're trying to do after you embed the nodes. And with this, I conclude. Thank you.